All right. Happy Thursday. Thursday, week 9. How crazy is that? We are almost done. So tonight we're finishing up chapter 10, and that's the last of the new material. Then next week, Tuesday, the test will open, and the all of the stuff is open. I have the project, everything is open. The only thing that hasn't been opened is the test, because obviously it doesn't open till Tuesday. Tuesday at 5 a.m., closes at Thursday at 11:59 as usual. And you're going to show your work as usual. I'm really excited. The stuff that we're doing today. Yes, I did say that. So what it says in the comments is that didn't I say that the last test people generally do better on? Yes. Usually test 3 is the higher score of the 3. And I think it's because chapters 8, 9, and 10 all kind of they all kind of rely on each other. They're really melded together really well. So we're going to do 10.2 and 10.3 right now. So 10.2 is very similar to 9.1 and 8.2. So all of that ties together. We're using a lot of the same concepts. 10.3 is very similar to 8.2 and 9.1. Wait, did I do that backwards? 9.1 and 8.2, or 9.1 and it's the mean, whichever ones are the mean. I really had it. It's all gone now. Anyway, 9.2 and 8.1. There we go. So we're going to be using a lot of the same stuff. For the mean, we're going to be using t-scores, just like we were doing with 9.2. And with the population proportion, we're going to be using the critical values. We're going to be using z-scores. It's all really tied in together. And there are questions on the test that tell you to show every step of a hypothesis test. And I'm going to show you what I'm expecting you to show me on the test. So that way you will get all of those points. Because it was kind of like, remember way back in test 1 when you had to show me your box plot and I graded it off of your work. That's going to be the similar where you're going to show me in your work all of the steps, and then what you type into the computer is just going to be your conclusion. So that's essentially what's going to happen here. So I have 100% faith in all y'all, and this is going to be a good test. So let's jump in. 10.2, we're going to test hypotheses about the population proportion. 10.3, we're going to test hypotheses about a mean. So I might have left a couple of slides from 10.2 that we already covered on Tuesday, but it's a good reminder. There's nothing wrong with going over a couple of slides the same. So let's dive in. And actually, I have exactly the same number of slides today as I had on Tuesday. That's kind of cool. All right, so remember point estimates. Remember that our p hat is the number of successes, or the number of individuals in our sample that have a certain characteristic, divided by the number of our sample size. So this is just our point estimate. It is the same thing we were using before. It is our estimate based on our sample, our p hat. Anytime anything has a hat, it's an estimate. So a sampling distribution of p hat, it's approximately normal with a mean, with our mean is equal to the population proportion. This is the new standard deviation. We're using the same one. This is the same one we were using before. Thankfully, that hasn't changed. And we can use this math if this right here. So these are the things that we need to know. So the samples are independent if 0.05 times our sample size is less than, I just don't write that. Our sample size is less than 0.05 of the population. So our sample size has to be less than 5% of the population. So however you write that, that's how we can tell they're independent. So what I would like you to, when you are doing when you're doing your hypothesis testing, you have to check these requirements first and show me that math. No, you don't have to show me it's less than the population size. Just make a statement saying it's less than 5% of the population. But show me the NP times 1 minus P is greater than or equal to 10. But remember, we only use that for proportions. All right. So we already kind of saw this, and so I'm just bringing it up again. If it's a two-tailed test, you'll have the words different. I'm going to write the words below. You'll have the word different. So it's not going to say that it's less than or greater than. It's just going to show different. For left-tailed test, it'll say something like less than, has decreased, smaller. Any words that mean that it's smaller than or less than. This is a left-tailed test. And then our right-tailed test is going to say greater than, larger, increased, or any other words that mean bigger than. This is all stuff we did Tuesday, but this, that we talked about Tuesday, definitely a good reminder before we jump in here. So I don't know about you, but it's been a long week. Whoops, didn't mean to do that. Okay, moving on. So this says that you're going to select a level of significance, but you are not going to select that. You will be given that unless you're using the hypothesis testing in your final project. You will be given your level of significance, and that alpha is the seriousness of making a type 1 error or the probability of making a type 1 error. So yeah, so you'll be given that number and it'll tell you significance level or level of significance or something like that. So that'll be given to you. So the test statistic. The test statistic is the Z-score based on your sample. I'm going to write this on here. It's the Z-score based on your sample. So remember this right here, that right there is that new standard deviation. Uh-oh. That's the new standard deviation. So we do our p hat, which is our estimate, minus our p naught, which is the population. So p hat minus p naught and divide it by the standard deviation. That's going to give us the z-score. This is the z-score that we are going to compare with the critical value, which is at the edge of our confidence interval. So when you are computing your standard deviation, you are going to use your p naught. You're going to use your null hypothesis because until we can prove or have evidence that the alternative hypothesis is true, we don't know it's true. So we have to assume the null hypothesis is true until somebody tells us otherwise. So you're using your p naught. P naught just it corresponds with our H naught, our null hypothesis. It just means your initial value or your population or the one you're comparing it to. Okay. This is just what it looks like when we're comparing it. So if this is I'm going to just use the middle one because it's right here. If this is my confidence interval right in here, if my test statistic lands me out here in the critical region, I will reject the null hypothesis. Reject the null. If my test statistic lands in here, I will fail to reject. Now, I don't care if you use the words fail to reject or if you just say we don't reject. Either way, but I want you to say whether or not you reject the null hypothesis. I want you to say that in your conclusion. Okay, are we good so far? We haven't done any math yet, but just making sure. Alrighty. So, for a two-tailed test, if I'm either greater than, if I'm greater than the positive or smaller than the negative, then I'm going to reject the null hypothesis. It basically, if it falls in the critical region, this is confusing, and I'm just going to move past it. I already told you how to compute the test statistic. We already were here. The thing is this right here. This is if my p-value is less than alpha, we will reject the null hypothesis. So the p-value is the probability of getting that z-score, our test statistic, if the null hypothesis was true. So I'm going to write this down. The p-value is the probability of getting our test of getting our test statistic, I guess, if um if H naught is true. So if that p-value is smaller than our alpha, then we reject the null hypothesis. If the p is low, reject the ho. I know I already talked about this, but I feel all of it bears repeating. Okay, moving on. Let's do an example. In 1997, 46% of Americans, whoa, something weird's happening here. Okay, 46% of Americans said they did not trust the media when it comes to reporting the news fully, accurately, and fairly. In a 2007 poll of 1,010 adults, 525 said they did not trust the media. This is our alpha. This is our level of significance. At a 0.05 level of significance, is there evidence to support the claim that the percentage of Americans that do not trust the media has increased since 1997? Is there evidence that it has increased? Okay. So if I was doing this on a test, okay, the first thing I would see, so this doesn't tell me it's a simple random sample. I would say a simple random sample not stated. That's what I would say, but it probably is. But I would state that it doesn't show that it's a random sample. So I'm going to just put, but still do the math. Not stated. I'm going to move this up because I'm going to need this room. So I'm going to move this. Okay. That was weird. Okay. Random sample not stated. The next thing I'm going to say is that 1010 is less than 5% of Americans. So I tested the 5% rule. Now, I don't care how you write it. If you just said 1,010 is less than 5% of Americans, if you wrote it in words, or you can just say our sample is less than 5% of the population, I'm fine with that. However you want to write it. Next, NP times 1 minus P needs to be greater than or equal to 10. So we have, yeah, so N is our sample size, 1010 times 0.46 times 1 minus 0.46. Let's math this out. And 10 times 0.46 times 1 minus 0.46. And I'm probably supposed to be p hat, isn't it? Didn't I just totally mess up? I think I just totally messed up. Hold on. Sometimes we have a day. Where is that? No, it's just p. Okay. I was good. I did fine. Sorry about that if I'm messing up your eyes. So this is 250.8, which is greater than or equal to 10. So we're good there. So make sure that you test all these three things. You're not going to have to do it with my open math, but do this on the test. Test these three things. Okay. The next thing, write your null and your alternative hypothesis.
Do we have to do that for every single problem on the test, or is there one specific one that we'll be asking to show all of our work, or can we do calculator for other ones?
Okay, so you'll have one that's proportion and one that is mean that you have to do this. Otherwise, you don't.
Okay, thank you.
And you will still be able to use the calculator. There is a calculator function that you're going to be able to use, but you just need to write down what you put in the calculator for that. And I'll get to that
Perfect.
in a little while. Yes. Okay. But you do need to, no matter what, write your null hypothesis. So my null hypothesis is that I think that P is greater than or equals, sorry, my P equals 0.46%. Remember, the null hypothesis is considered true unless we can show otherwise. I forgot to find my p hat, so I'm going to do this up top because I want room. P hat equals 525 divided by 1010. Put that in my calculator. All of this is going to be printed on the next screen, but you know how I do. There we go. So my p hat is 0.52. I'm going to need that in a little bit. My my alternative hypothesis, we think that P is greater than 0.46 because it says has increased. So we think it's greater than. This is a left tail or a right-tailed test. Man, I almost messed that up. This is a right-tailed test because it has greater than. Okay. This is all the not math stuff. This is all the just setting up the problem. So, I think I'm gonna do both ways. I'm going to do the test statistic versus the critical value first. So I'm going to do that first. So I need to find my critical value, which is the edge of my confidence interval. So I'm going to write this down. Your critical value is just going to be Z sub alpha. Because it's not a two-tailed test, it's not divided by two. Right. I just wrote that down there, critical value. I'm going to move this thing up to the top. Hopefully it won't be in the way. I wish I could figure out how to get rid of that. I need to use Google. Okay. I'm going to jump over to the T table or the Z table right here. Take a look at this. I love this. These are the basic levels of significance. So 0.05 right here. It's a right-tailed test. 1.645. That is my critical value. This tells me how many standard deviations away from my proportion, my null hypothesis, the edge of that confidence interval is. The edge of the confidence interval is 1.645 standard deviations above that proportion, the population proportion or the null hypothesis. So good thing to note, every time you have a left-tailed test, you'll have a negative z-score, a critical value. Every time it's a right-tailed test, it'll be a positive. For two-tailed, you'll have the same number, but both the positive and the negative every single time. All right. I'm going to jump over here. Okay, I have my z-score. This is my critical value. Okay, next, I need to calculate my test statistic. So my test statistic, remember, it is p hat minus p naught divided by square root of p naught times 1 minus p naught divided by n. Okay, you can, if you're really careful, you can put this whole thing in your calculator at once. I'm going to put the numbers there. So my p hat is 0.52 minus 0.46 divided by square root of um, 0.46 times 1 minus 0.46 divided by my sample size. That's a lot, but I'm going to show you how I put it in my calculator because parentheses are your friend. So I'm going to calculate that z-score. Give you a second to write it down and then I will go calculate it. I feel like this is a good place to show you how I put things in the calculator. Okay, here's my calculator. Super important. Parentheses around your numerator. Well, you can't see that. 0.52 minus 0.46. I can tell you with absolute certainty, if you do not put parentheses around the numerator, bad things happen and your answer will be wrong. Okay, now square root, second x squared, parenthesis, 0.46. I'm going to open another parenthesis, 1 minus 0.46. I'm going to close both those parentheses, then hit divided by 1010. There we go. I'm going to hit enter. So my z-score, my test statistic is 3.83. Okay, let's go jump back here. So if I was going to draw this, I'm going to show you what it looks like when you draw this. Okay, my 46%, this is my 0.46 right here. This right here, I moved to the right 1.645 standard deviations to get to the edge of my confidence interval. This area out here, this is the critical region. My z-score, or my test statistic that I just got, is way out here. 3.83 standard deviations above the mean. It's way out there. So, because it is way out there in the critical region, I would reject the null hypothesis. I have sufficient evidence to show that that the actual number of Americans, actual percent of Americans who don't trust the media is greater than 46% because that z-score is way out there. You have questions so far?
So just to reiterate, we're not following the 2 standard deviations rule here. We're following that level of significance
Right.
z-score.
Yes. When we did that Tuesday, the 2 standard deviations, it was because we didn't have all this math yet. And it was just like a real quick example based on empirical rule. So, okay, we're now going to, okay. So it would be different. So Kate, if I would have gotten 1.645 as my z-score, then I would have said that we don't have and I would never give you one that lands right on that mark. But if I got 1.645, I would fail to reject the null hypothesis. If I got 1.646, I would reject the null hypothesis. So even this slight bit to the other side, you reject the null hypothesis. That is the limit. Just like technically they can give you a ticket for driving 1 mile over the speed limit. Not that they would, but it's still considered speeding. No, it's good. No, it was not a dumb question at all. I'm sure somebody else had that very same question. So it's not dumb at all. Keep asking them. Okay, we're going to do the z-score thing, or we're going to do the p-value now.
Can I just ask a quick question about how you should best state that? So the statement would be 3.83 is outside or higher than
So here's probably, you want me to write some words?
Yeah.
Everybody, can I erase my picture? Okay. This is probably what I would do. Um, since I'm going to write it in a different color. We've already used that color. There we go. Since the test statistic of 3.83 is greater than our critical value, we have sufficient evidence if I could spell it, that the proportion of Americans who do not trust the media is greater than 46%. Therefore, I'm out of room. I'm going to make this smaller. Thankfully, I have tools. Oops. Because I ran out of room. Okay. My little N went with it. Therefore, uh-oh, I need a pen. We reject the null hypothesis. Now that's a lot of words, and it's a lot. Now I am absolutely okay with you just saying, on your conclusion on your test, if you just say, we reject the null hypothesis because the test statistic is greater than the critical value. If that's all you said to me, you would get full credit on that. Well, I mean, you'd have to show me everything else as well, but I would be fine with that conclusion. This is kind of the formal conclusion. If I was writing a paper, this is what I would write.
Can you repeat that one more time, the simplified version, please?
Yes, you could say, since my test statistic is greater than the critical value, so I reject the null hypothesis. That would
Thank-
be fine. Yeah. I'm okay. As long as you justify, I want to hear the word reject or do not reject. I want to hear those words or fail to reject. I want to hear those words, but I want you to tell me why. I need you to justify that by saying the critical value or the test statistics greater than the critical value, or the p-value is less than the alpha. I need you to justify it, and then I need you to tell me whether you reject or fail to reject. Those are the two pieces of your conclusion that I want. And I love this beautifully written out thing, but I know you only have 90 minutes. And I know testing is stressful, so you don't want to have to remember flowery words. I am okay as long as you justify and are clear. That's it. Okay. Are you guys ready for the p-value? We're good? Okay. I'm going to do the p-value on this one. Okay. All right. Get rid of this. So with the p-value, I'm going to look for the probability that um, my test statistic is greater than greater than or equal to 3.83. This is what I'm looking for. Or I'm looking for the probability that I would get a z-score greater than 3.83, given that I have this right here. Or given that this is my test, actually, yeah. So, or I'm going to back up on this. I don't want this. I'm sorry. I hope you're using pencil. I'm actually going to use this instead. I'm going to use the p hat. But the probability I would get that p hat given this right here. So what I'm going to do is normal CDF. Did I just lie? Can you guys like, let's just like erase the last 6 minutes of this or 60 seconds here. I just lied to you again. My goodness.
I found that you can do normal CDF to get that number, but you can also put the whole thing in the calculator and do it that way to get the P
Well,
number.
I am going to use normal CDF, but I'm going to use normal CDF with the Z-scores, and that's why I messed up. So normal CDF, um, 3.83 to infinity, 0, 1. That's really what I meant to do. What's the probability of getting? See, what I was trying to avoid is I was trying to avoid using this standard deviation right here, which you can do, but I can also do this. So
And this is finding the p-value. Is that what we're doing?
yes, we're finding the p-value. So I'm going to go back to my calculator. I'm not wondering if they do that, how they do the, yeah, okay. Okay. So you guys know this, but I'm just going to do it anyway. Normal CDF. So it's 3.83. And my upper is 1E99, 0, 1. So that is, okay, there's one of the reasons I wanted to put this in my calculator is because I wanted to remind you what this means. This is scientific notation. So what this means is 6.4 times 10 to the negative fifth power. I'm going to write it on my screen and then I'm going to bop back over there. So I have 6.409, and I'm not going to put all those letters, E negative 5, all those numbers. So when I bop back over here, that was a 5, not a 9, right? Yep, okay. So what this is telling me is that I need to move my decimal place 5 to the left. So what this is going to look like, that's the number, that's the probability. That probability is basically 0. I mean, I would pretty much call that a 0 probability. There's almost 0 probability of getting that Z-score. So this right here, uh-oh, as I just erased it, this right here is less than my alpha, which is here. So this is less than 0.05. So you would be able to say, so just everything that I said before, except for instead of comparing the critical value and the test statistic, I'm comparing the p-value to the alpha. So I would say that since we have a p-value of 0, I could call this 0, which is less than our alpha of 0.05 or less than our level of significance. I can reject the null hypothesis. So you can do it either way. If P is low, reject the hoe. We're
Can
rejecting
you repeat that again? If the p-value is less than,
then our level of significance,
okay, less than,
or you can say alpha. I'm perfectly okay with you just saying alpha. Either way, level of significance or alpha. If the P value is less than our level of significance, we reject the null hypothesis.
So you still have to do all of that math though, even though you did the normal CDF. Like the normal CDF is just like an additional step, or
That's to get the P value. So if you are doing things by hand, if you're doing it by hand, you are definitely going to want to use test statistic and Z-score and critical value. If you're doing it by hand, because doing the p-value is just one extra step. And so generally, if I'm doing it by hand, I'm just going to use my test statistic and my critical value. However, if you were doing this in your calculator with the function I'm going to give you in a few minutes, the p-value makes more sense.
okay, because you can't get the p-value without doing all of that math in this instance.
Right, exactly.
Okay.
Doing it by hand, you can't. I mean, and I could look at my Z table. Hold on a second here. Even though it's like the right side instead of the left side. So 3.38, where does that land? Okay. So 3.38, I would have to do 1 minus this, but it's still, you could look at this and be like, yep, or 3.83. See, 3.83 isn't even on my Z table. It's so far off. You could tell it's going to be basically 0, right? Because it's so far off my Z table. Okay. So I'm going to go to this right here. It says it's a simple random sample, but they didn't tell you that. This is the stuff that I went through at the beginning that I did at top, showed that my NP times 1 minus P is greater than 10. I said that it says it's a simple random sample, but they didn't tell us that. But I'm not going to, whether you say it is or not, I'm not going to mark you down. Just do this. Do this piece. Do this piece. Tell me that you're less than 5%. I don't even care if you say the assumption of independence is met. Just say it's less than 5% of the population. Give me these 3 checks. These are 3 things I want you to show me in your work when I say show me every step. Because that's what I say that I said, show me every step. So I want you to show me these 3 things. So I would, if you have the PowerPoint printed out, make a little note to yourself on the test to show these 3 things. Then next, you definitely need to show your null and your alternative hypotheses. You don't have to tell me the level of significance. You're going to be using that. Here's your p hat. Here's the test statistic. I mean, we already did all this.
Professor Kleitz,
Yes.
can you refresh my memory if the Z value is not on the table that we use, how we find that? Like if the level of significance is not either 0.1, 0.05, or 0.1, how we find what the critical value is?
I was absolutely going to get there, but I can totally show you.
Sorry about that. Thank you.
No, don't apologize. I love it when people ask me before I even get there. So let's pick a random one. So it really depends on if you're right-tailed, left-tailed, or two-tailed. But I always just, for right-tailed and left-tailed, I just remember that left-tailed's always negative and right-tail's always positive. So let's say we have really weird one. Let's say we do have 0.15. Okay. So if it was 0.15, I need to think about it. If it is right-tailed, I'm going to have 0.15%, 0.15 or 15%. I'm going to have 15%. I want this gone. 15% right here in this tail, right? So I can use 0.15 in my inverse norm. It's just a z-score. So I can use 0.15. But remember, let's see here. Remember that it is because I am using a right-tailed test, this has to be positive. So even though this is a negative, it's a right-tailed test, I'm going to use positive. If it's a left-tailed test, use negative. Just remember that. It's somewhere in your brain. Write it down. Or I can write it right here.
Thank you.
Let me see here. This isn't really the best page for it. Right-tailed test. Critical value, always positive. Always, and I ran out of room, positive. Okay, left-tailed test. Critical value, always negative. Now I can't spell. I'm going to write it down at the bottom, the next one. Two-tailed test. Plus or minus z-score. You're going to use both the positive and the negative of whatever z-score you get. So I'm going to do a two-tailed on using inverse norm. Okay, I'm going to move this. Let's move this up here. I guess I did want it up there. Well, look at that. I didn't mean to do that. Let's stop that. Let's try it again. There we go. Okay. So I'm going to do a two-tailed now. So let's still say our significance level, we still want 15% for our significance level for a two-tailed test. So that is not a pen. So the important thing here is to remember if it's a two-tailed test, 7.5% is here, 7.5% is there. So I need to use inverse norm with 0.075. You have to cut that in half. If it's a two-tailed test, cut your alpha in half before you put it in your inverse norm. And then you're going to use both the positive and the negative. And on the test, I will absolutely use one of the ones on the bottom of your Z table. All right, are we okay? Can we move on? We're good?
Thank you so much.
I am sorry, I'm behind on the writing of the notes. You
Okay.
cut, so what's the value that you cut in half?
The alpha. So for
Okay.
example, this one right here. So let's say instead of a right tail test like we have here, let's say I had a two-tailed test, I would put 0.025 into my inverse norm on a two-tailed test. Just like remember when we were doing like center 90%, it's the same concept.
Yeah, okay.
And so that's why notice if I go back here, notice that the critical values, if I look here, so the hypothesis testing critical values, they're the same. So look at the 90%. Remember that our confidence intervals were basically two-tailed, correct? It's the center 90%. So my critical value is 1.645. Take a look at my two-tailed value. It's the same. My two-tailed values match these levels of confidence because the two-tailed test essentially uses that center confidence interval that we created. It's all connected. That's one thing I love about chapters 8, 9, and 10. It's all connected. All right. Let's pop back there. Okay. Here is the their conclusion. Their conclusion based on the test statistic. The test statistic is greater than the critical value. See this right here, step 5. If you wrote these exact words on your test, step 5, I would absolutely be 100% okay with it. You'd get all the credit for the conclusion portion. So step 5 right here is beautiful. Okay. I think they give us the p-value. So here they calculated the p-value. They didn't show you how, but that's okay. And then they got the approximately 0. The p-value is less than the level of significance. We reject the null hypothesis. Once again, step 5 right here. Perfect wording. I will accept it. I want you to state the words of whether or not you reject the null hypothesis and why. Okay, any more questions before I move on? You ready for a calculator function? Oh, this is yeah, they just gave us a big thing. How come it doesn't give me the calculator function on here? What the heck, man? Okay, it's okay.
I have if it's okay, it's a binome CDF. I printed out them out, so I have a slide with that on it.
Yeah, I don't know why I took that slide off. I don't know where it is. It's okay, but I have it. I mean, I will show you. So your calculator function, let's go there. Clear, clear, clear. Okay. So I will write it on one of these slides. Don't worry, but let's go there. So hit the stat button and go over to tests. And we're going to one prop Z test, one proportion Z test, because this is hypothesis testing. One prop Z test, hit enter. Okay, is this the right? No, it's not. It's not the exact numbers. Okay, I need to go back to my screen that has numbers. So we have our 0.46, that was right there. 525. So 525 people had the characteristic out of 1010. Now, I am notorious for choosing the wrong answer all the time. I frequently choose the wrong one unless it's different. If you choose the wrong one, it's going to be usually a very large number. Like for example, let's check it out here. So it says it's going to be greater than my p naught. So I'm going to choose that one, hit calculate. So notice my p-value. So this is my this right here is my test statistic. It will not give you a critical value because it doesn't know your critical value. It doesn't know your significance level. So it can't tell you a critical value. But this Z right here is your test statistic. This is your p-value right here. And then this is your p naught or your p hat. So this is my the proportion of my sample right there. So this is all of the information you need to do either one, to use your p-value to test against your alpha or to use your test statistic to test against your critical value. So it's one prop Z test. I'm going to hop over to another screen. I'm going to write this down real quick before we and then I'm going to go back to the other screen because I'm going to write down which one is which tail because I get this wrong every time and I happen to get it right one time. So I'm going to write this down. Okay. And then I'll show you my screen. Because almost always, let me show you what I always do. I'm really bad about choosing the wrong one. So if I chose the wrong one here, if I chose that one instead, see, I look at my p value, it's 0.9999. If I end up with something like that, I'm like, well, I chose the wrong one. And I will go back and fix it and choose the other one. So if you end up with like a super long p-value and your z-score, so see how my z-score is 3.8? If my z-score is 3.8 and I have a p-value of almost 1, I chose the wrong tail. Now, if I would have had a z-score of 0.6, I would expect a large p. I would expect that because that z-score is not so far away from the mean. But in general, if you end up with a really big number here, you probably chose the wrong one. So here we go. I wrote these down for you. So the not equal to, that one's easy. That's a two-tailed test. This less than here, that's the left tail. This greater than here, that is the right tail. And we use one prop Z test for the proportions. I'll let you write that down while I take a drink.
On the first demonstration you gave with your calculator and you said it didn't give us a z-score, is that what you said?
It doesn't give us the critical value. It gives us a test statistic.
What would it look like? Does it not have a z when it's a critical value?
No, the critical value, they're both z-scores. I'm comparing two z-scores. I want to put this in doing the right thing. So the two z-scores that we get that we're comparing with each other, yes, I will definitely. So Kate, are you talking about these ones right here, these values? Okay, good. I will write them down also after I answer this question. Okay. So we find a critical value. That's what we get off of this table right here. The critical value is the edge of our confidence interval based on our significance level. So it's just telling me where the safe zone ends, where the critical region begins. And that is based on the alpha. It has nothing to do with my sample. It is based on the alpha. The z-score that we get here, this z-score, is the test statistic. This is when I take my sample and I find a z-score with comparing my sample to the original proportion. I get a z-score for that. It tells me how many standard deviations is my sample away from the original mean, which is, or the proportion, which is that. This is the test statistic. This one is going to tell me, am I outside of my confidence interval? Am I in the critical region, or am I in the safe zone? That's what this is. This is the test statistic. So those are two z-scores, a critical value and a test statistic. And those are the two things we compare.
So you'll need the z-score regardless,
Yes,
and that is what you find on the table.
yes,
Or you use the inverse norm.
yes.
Gotcha.
Okay, I'm going to write these down and then I will label them so that, and I'm going to be rounding numbers because it would be really dumb of me to write every number out. They don't pay me enough for that to write every single number out. I'm kidding. Okay. Okay, I'm going to go back over. Here we go. Let's get a different color because colors are fun. This tells me this is my p hat. That's what that is. Nope. I just lied to you. This is my p. That's the p. This is the null hypothesis. This is what we're comparing to. That's in the null hypothesis right there. This right here is the test statistic. This is my z-score using my sample. That's the z-score using my sample. This is your p-value, which is the probability of getting the value of your sample if the mean is what the mean says it is, basically. If my null hypothesis was true, the probability of getting the sample I have, that's what that is. So if it was really 0.46%, there's a 0 chance that I would get the 52% that I got. This right here is my p hat. I think that already says p hat. I wrote p hat. It doesn't say that on the screen. What does it say on the screen? Oh, it does. Okay. Uh-oh. That's from my sample info. That's the proportion of my sample that has whatever characteristic. And then this is just my sample size. Any questions about that? All right. I'll give you a second, and then we'll move on once again. I just have iced tea. It's iced tea. It's safe. It's not anything weird. Some people see because it looks kind of brown in my screen. They question. Okay, moving on. All right. If you keep track of that sort of thing, we are now in 10.3. We are now in 10.3 if you keep track of that stuff. All right. I know some of you struggled a little bit with your with the t values. So it's probably a good thing that we are revisiting t values. It's probably good. All right. So when we are using the mean, when we are using the t values with the mean, we have to use the calculator for the p value. You can't just throw it in normal CDF. It doesn't work like that. I do think that there might be. Is there a normal with hold on. I think there might be a normal with T's. No, there isn't. Oh, there is a T PDF. We're not going to do that. We're going to find our p-value just using our calculator. We're not going to try using normal CDF or anything like that. But I do have a good calculator function and it works and we like it. So we use the same types of things. We're going to get a critical value. We are going to get a test statistic. And we are going to critical value, a test statistic, and we're going to get a p-value. We're going to get all the normal things, and we're going to compare them exactly the same. Once again, we're following a t-distribution with n-1 degrees of freedom. So when we get our critical value, we are going to use n-1 degrees of freedom. So you'll use either inverse t or the t-table. All right. So remember, you don't have to remember all this. The t-distribution is different for different degrees of freedom. It depends on your sample size. It's centered about 0, symmetric about the mean, all that crazy stuff. And we don't even care about all that. We don't care about all that. Okay. So what we're going to do, these again, this is the stuff you're going to have to show on your, you need to show this on your problem when you're doing on your test. When I say to show all the steps, this right here is this, what happened? I don't know what happened. Okay. Is that n is less than 0.05 of the population. So n has to be less than 5% of the population. We do need to have either a larger sample size or it has to be normal. So the population has to be normally distributed or a sample size larger than 30. So you'll have to tell me one or the other depending on what I give you. Now, it is possible I could give you a sample that isn't greater than 30, and it doesn't state that population is normally distributed. So you'll just have to state that. Just state that it is unknown if the population is normally distributed, and I have a small sample size. Just do the math anyway, but just state that. And the same thing with the simple random sample. So even if it doesn't fit all three of these things, you're just going to state what we have and then move on. Just still do the math. This is all the same. We're just using mean instead of population for my two-tailed, left-tailed, and right-tailed. It's all the same. Okay, my test statistic. Once again, we will have a level of significance that we are given. You will be given the level of significance. This right here is your test statistic. It is the same thing we were doing in the last section. This right here is the new standard deviation when we're using mean. This is the new standard deviation. This is my sample mean, and then this is my H naught. This is what we're using for my null hypothesis. So you take the sample minus the null hypothesis and divide it by the new standard deviation. That gives us our new t-score or z-score, basically like a z-score, but with a t. So that gives us that new one. This is what we compare to our critical value. Okay. All of this is the same. All right, the p-value, we're not going to use this for the p-value approach. We're going to just use the calculator. So ignore the use the table 6. Use your calculator. Okay, let's move on. Once again, if the p-value is less than alpha, we reject the null hypothesis. And then you state your conclusion using the same words that we used in the last section. Okay. So if it's not going to hurt too much if there is a little bit of, if your population is not perfectly normal, or if it's not perfectly normal, that's okay. If it's mostly normal, we're fine. Smaller sample sizes, or if there's outliers, we generally don't use this. However, I think the sample size on the test is small because I wanted you to use data. So you're just going to have to say the sample size is less than 30, and you're just going to call it good. Because I didn't want to give you a 30 sample size. I wanted to give you something smaller. So I think, I don't remember, but it's okay. That what's important is you doing the math and stating your conclusion. All right. So we're assuming that the resting metabolic rate of a healthy male in complete silence is 5710 kilojoules a day. One of the great things about having people who work in the healthcare industry in my class is somebody a couple of probably 3 or 4 terms ago told me that that was kilojoules, and it makes me really happy that I know that now. Just letting you know. So we have 45 healthy males. I'm assuming that's simple random sample, but it doesn't tell me that. Their mean, the 45 that we have, their mean was 5708. Their standard deviation was 992.05. So we want to know, at a significance level, is there evidence to show that the resting metabolic rate is different than 5710 kilojoules a day? Is there evidence to show it is different? So once again, as I stated, it doesn't tell us that it was a simple random sample. We are going to assume it's a simple random sample. My sample size is greater than 30. So that's good. So my sample size is greater than 30. So based on the central limit theorem, we can continue to use this. We can say that it is normal. You don't have to remember that it's the central limit theorem. You can just say sample size is greater than 30. If all you did was write those words, we're good because we're just showing it's normal. Okay. Next thing we're doing is 45 is less than 5% of our population. We're good there. One of the reasons I'm just saying it is because this is a lot of words, not much room for me to math. Okay. Let us, before I even find the critical value, I'm going to calculate the test statistic. Then we'll jump and find the critical value. So my test statistic is going to be my X bar. I'm going to write this. X bar minus mu naught. Oh, I didn't write my, I may write this and then I will, silly me. That's not what I want. S divided by the square root of n. Okay. I forgot to write my my hypothesis, my null and my alternative. I'm writing it up top. My null hypothesis is that the mean is 5710 kilojoules per day. My alternative hypothesis is that the mean is not equal to 5710 kilojoules per day. So that's my null and my alternative hypothesis. Don't forget to write those down. Now let's calculate the t score, the t naught, which is my test statistic. I have my 5708. Oops. That's ugly. 5708.07 minus 5710 divided by S, oops, I need that actual value, 992.05 divided by square root of 45. I'm going to show you how I put this in my calculator. You need lots of parentheses. I'll let you write it down real quick. Okay. It's clear. Okay, numerator. Numerator is 5708.07 minus 5710. Close my parentheses. Divided by parenthesis 992.05 divided by square root. That's squared. Why did I do that? That's a weird place to put a, okay. Square root 45, arrow out. I need to use the arrow to get out of there because otherwise I'm still underneath the radical, and then close my parentheses. So you just use the right arrow will get you out from under the radical. Hit enter. So my test statistic is negative 0.1 or 0.13. I bet you can guess what's going to happen here, because remember that test statistic is a z-score. So a z-score that is really close to the 0 right there means I'm sitting right next to the mean. I'm probably going to fail to reject, but we don't know for sure yet. That probability is probably going to be pretty high. Okay. So here's where I am right now. So now that I have my test statistic, I'm going to go look for the critical value. So the critical value, once again, we're going to use n minus 1 degrees of freedom. So I'm going to jump back to my screen. Since this number is greater than 30, the t-score is going to be really close to what it would be as a z-score. And you're going to see that my t-table doesn't have 45 or 44, but it's okay. So let me see here. So my t-table, let's go down here. See, it doesn't have a 44. Let me see here. It goes from 40 to 50. So it doesn't even have a 45. Just a second, I need to get my my level of significance. My alpha. Whoa, that was weird. My alpha is 0.05. Because this is a two-tailed test, I'm going to take, let's see. I'm going to take the 0.05 and I'm going to divide it by 2. I get 0.025. This is what I'm going to look for. Because it's a two-tailed test, I have to cut that in half. Okay. So I'm going to go back over here. Where is that? It's right here. So I'm going to scroll down. Okay. So I have 40 and I have 50. So I'm going to go halfway between 40 and between these two numbers. So my critical value, $2.015. See, this is a case where I probably would just use inverse T on my calculator if you have inverse T. Otherwise, just finding what's smack dab in the middle of these two values will work. I know we do 44, but it's not going to be that far off. Here's what I got. I got 2.015. Let me show you what happens when I use inverse T. Second vars, inverse T. It's the area I'm looking for, 0.025. My degrees of freedom is 44. See, I got 2.015. See, it's still 2.015. Yes, it's negative. We're going to ignore that. We need the positive and the negative. But it's still, because our sample size is greater than 30, it's not a huge difference from number to number. Okay, we're back here. Okay, now I'm going to draw this so that you can get a better understanding of what's happening. Okay, so I have 0.025 over here, 2.5% there, 2.5% there. Okay, this is my mean. And my edges, this right here is plus 2.015. This over here goes to minus 2.015. That's the edge of my confidence interval. All I did was basically create a confidence interval. So now my test statistic, this right here, my test statistic is basically right here. It's practically right on top of my mean. This right here is the t-score, negative 0.013. So clearly it's in the safe zone, and clearly I would fail to reject the null hypothesis. I would state my conclusion would probably say, whoo, Whoa, sorry about that. My conclusion would probably be that, whoa, something about negative 0.013, since my test statistic of negative 0.013 is greater than the critical value of negative 2.015, I fail to reject the null hypothesis. It's probably what I would say. So if my test statistic is a negative z-score or t-score, I'm going to compare it to the negative critical value. If it's a positive t-score, I'm going to compare it to the positive critical value, if that makes sense.
I'm confused as to how you assumed that it's positive when you used the inverse t and got a negative number.
Well, it's positive and negative because this is a two-tailed test. We use both of them.
Oh, okay.
Yeah. If it was a right-tailed test, I would use the positive. If it was a left-tailed test, I'd use the negative. Since this is two-tailed, we use both.
Thank you.
You're welcome. You ask all the good questions. Okay.
I've got a lot of them.
It's okay. It's okay.
Where
right.
you wrote 2.5 on your graph, is that stating that at 0.025?
Yeah, it's 2.5%.
Yeah.
It's just what I meant. But yeah, 0.025. Yeah. I converted it to a percent because for some reason when it's on my curve, I see it as a percent. But when I'm using it for other things, I use it as a decimal, and I'm sorry about that.
But we're talking about the same kind of values as that
Yes.
critical value you found, right? Okay.
Okay. I'm gonna jump through because we're gonna get to the calculator function with mean. The calculator functions tend to be more useful because we can't use the p-value. We don't have an easily calculatable p-value. I'm going to go through the printed out stuff. So yeah, sample size is large, so you can follow the test. Here's my null and my alternative hypothesis. They found the same t-score we did. And so what they said is, since it's a two-tailed test, notice that they used both the positive and the negative. So they use both the positive and the negative, which is great. And it shows our test statistic. This is a great way to do it also. Since the test statistic is between the two critical values, we fail to reject the null hypothesis. That's another way of wording it. I'm okay either way. And since I'm the one grading your paper, either way that you do it is fine. So this is for the two-tailed test. So we're going to get a p-value. So this even says by hand method is not great. We're going to use the calculator. This is the function that we're going to use. It's t-test. And I'm going to show you how to use that. And this will give you a p-value. So let's jump over to the calculator. All right. It's found in the same place. So you do stat, go over to tests, and it's the second one down. It's t-test. I'm going to hit enter. Okay. This is similar to when we were doing confidence intervals. You either put the data in and it populates it for you, or you do stats, which is what we have right now. I need to go back to the page where I have numbers. And so we have stats, so I'm going to keep it on stats. My mean was 5710. That's and notice how it has the not. So the little O right here means that was your initial mean. That is not the mean that they give us. That it's a sample. That is the initial mean. The sample mean is right here. It's an X bar. So that was 5708.07. My standard deviation, 992.05. And my sample size. Remember, we need the sample size because we use the n-1 degrees of freedom for our test statistic. This is a two-tailed test, so I'm going to use the easy one, the two-tailed, and then we're going to go down to calculate. I love when their numbers match mine. So I'm not concerned about the big P value here because my test statistic was so close to zero. I mean, it clearly is like right on top of the mean practically. So I would expect that. So this is telling me this is my test statistic. Here's my p-value. There's the mean and the standard deviation and my sample size. Questions? I do have another example. But here I would say because my p-value is greater than alpha, we fail to reject the null hypothesis. So
Can you go to the screen where you're loading in your information and tell us what all those values are?
yes. Okay. So this right here is my null hypothesis mean, the original mean that we had. That's from the null hypothesis. This is the sample mean. This is the mean from those 45 those 45 individuals that I polled or I got their RMR, whatever it is. This is the standard deviation from my sample. It's a sample standard deviation. This is my sample size. It was 45. And then this is the same meaning as when I was doing the proportions. It just has a mean there. This is saying not equal to that we use when it says different. I can tell you that if you decided to have it draw, it's going to give you a nice curve and it's going to shade it in for you. And you're going to look at that and say, well, that's not useful. So if you decide to draw it, I mean, it's pretty, but that's not useful. And I hit calculate and it gives me that.
And what's the label for that first one?
The first one is just, it says mean is not equal to 510. That is listing my alternative hypothesis. That's what the very top thing says. My alternative hypothesis is that the mean is not equal to 5710. All right, can I move on? Are we okay? All right. In our right here, we have a sample right here of United States Mint's quarters. We say that according to the United States Mint, the quarters weigh 5.67 grams. A researcher is interested in determining whether the state quarters have a weight that's different from the 5.67 grams. So what they did was they took the quarter weight and they're like, you know what, I'm going to take those state quarters. You guys remember those state quarters that have all the different states on them? And this researcher thinks that it's going to have a different weight. They think that the state quarters are different and that they're going to have a different weight. And so that's what the hypothesis is. So we have 18 state quarters here. And we're going to put this in the calculator because no matter what, I need to get my mean and my standard deviation from this. Even if I hand calculate, I need the mean and the standard deviation. So I'm going to go to my calculator and I'm going to put it into my stat and my L1. These 18 quarters. Oops, I need to go hit clear. Okay, I'm going to put these in. I'll do it slowly so that you can go with me if you'd like. Also slowly because I'm just slow. $18 doesn't seem like a lot until you have to type it all into your calculator. It's also not as fast typing them on the computer as typing them into an actual calculator. Got all mine in there. I'll give you a second if you were following behind me.
Someone is at the front door.
Nobody's at my front door. My Alexa connects to my daughter's Alexa. We can't get them disconnected, and she doesn't live with me.
I'm not quite sure how to help you with that.
Alexa, stop. So when somebody rings her front door, it tells me here. Okay. So do you guys want to just jump straight to the calculator function, or would you like me to hand calculate again first?
Calculator, please.
Just calculator? Okay. Because you're all like, I'm not even going to mess with that hand calculation. Now, if you wanted, real quick though, if you wanted to do the hand calculation, if you do one var stats, it is going to give you your mean and your standard deviation. So here is my sample mean, and there's my sample standard deviation. Make sure you grab the sample standard deviation and not the population. So if you were going to hand calculate it, there's those values. Okay, so we're going to go to stat, over to tests, and go down to t-test. We have data in our list, so we're going to go there. But I do, however, need to put something into it does not know what my null hypothesis is. So I have to put that value in because the calculator does not know what my null hypothesis is. So that's what you're putting in mu naught. Put your null hypothesis in there. And then your L1 is where I have my data, and frequency is just going to be 1. And this one is not equal to. So I'm going to put it on not equal to. Then go down to calculate. I'll give you a second to catch up. And hit enter. All right. So here's what I have. Mu, this is my alternative hypothesis. Mu is not equal to 5.67. That's my alternative hypothesis. My test statistic. So this is the t value that we would be calculating. This is the t value based on your sample, 2.75. The p value is 0.013. I'm gonna write these down. Hold on a second here. I just realized writing them down is a really good idea. .75. My p-value 0.01. I'll call it 0.14. And the standard deviation, the standard deviation right there is just the standard deviation. It doesn't even really matter. Okay. And so this is my sample standard deviation. This is not the new standard deviation. This is just the sample. And then this is my sample size. So I'm going to pop back over to the other screen. Okay. So if I was comparing this to the alpha, notice my p-value is significantly smaller than the alpha. So I would be able to say, since my p-value is less than alpha, I would reject the null hypothesis. However, if you wanted to, if my open math or you particularly wanted to use the test statistic compared to the critical value, whoa, I'm going to use the critical value based on half my alpha because this is a two-tailed test. So once again, my alpha is 0.05, but I'm going to do alpha divided by 2, 0.025. My n value, my sample size is 18. So I'm going to get my critical value using the 0.025, and I'm going to use a degrees of freedom of 17. I'm going to subtract 1. So let's go back over here. So 0.025 is this column, and I'm going to use 17. So it's right here. So my critical value I just lost it, is 2.11 2.110. Okay. So my t value is greater than this critical value. So the critical value, I should actually, one second here. Move it over. My critical value is plus or minus, because we need the positive and the negative. My critical value is 2.110, and my t value is greater than the positive, right? It is outside of that region. It's in the critical region. It's outside of that confidence interval. So I could state that my test statistic is greater than the critical value of 2.110. Therefore, I reject the null hypothesis. Or you say that your p-value is less than your level of significance or less than alpha. Therefore, I reject the null hypothesis. That's the two ways you can do it. You're always more than welcome to do both of them to check yourself, but you don't have to do that. Okay, questions before we move on? We're almost done. Okay, so I had something. It was really good. Maybe it wasn't really good. It's gone now. Okay, so what I want you to show in your work, if you do one of these, what I want you to show in your work is I want you to say that you did t-test. Like you would tell me you put t-test in your calculator. And I think it wouldn't be, I mean, at least write down what you got for a t-value and a p-value when you do your t-test. There's a lot of t's and p's and everything. So write down what you got for the t-value, what basically the results that you got. So go back to the screen, my calculator. You don't have to write everything on this screen unless you want to, but I want these two things. I want the t-value and the p-value. If when you're showing every step, I want these two things. I want you to write those two things down so I can see what you got in your calculator. This will be really useful if you typoed. Because if you did everything correct, but you have a typo in your list, then these numbers will turn out wrong, and I will recognize that you had a typo. And then you'll probably lose less points than if you don't show me anything of the output, if that makes sense. Okay. So I'm going to go to the conclusions. Oh, this is just a lovely little plot. It doesn't matter. Okay. So this was our t-value. We already did all of this. I forgot to write my null hypothesis and stuff, didn't I? Because I was all excited. I have my null hypothesis. See, I got it all excited and I didn't do it. Equals 5.67 grams. And my alternative hypothesis. That was great. Not equal to. I frequently, when I'm doing my own math, I'll like forget all of the early steps and just get excited and jump into the math. And then I go back afterwards and I pretty it up and do things like write the null hypothesis, write all of the check steps. I'm really bad about not doing the check steps before I do the math because I get excited. I just love the math. I know, I'm weird. Fully aware.
Of the check steps for that specific equation, like this problem, when we're writing our conclusion, would you want us to include that we can reject the null hypothesis, however, the sample size is really small?
Well, I'm this yes, but okay, I'm going to show you. I did not teach you how to put things like I'm going to show you this right here. So this right here is the you can put a box plot into your calculator. This shows that there's no outliers. This shows that it's not bad. This also shows that it's kind of that way. I would probably, personally, I would look at this and say there doesn't appear to be any outliers, therefore I can use a sample size of 18. I might say that, but you can even just state that the sample size is less than 30. I'm going to accept it if it doesn't specifically tell you it's a normal. It's normal. I just want to make sure that you're checking. I want to make sure you're aware that we should have a sample size of 30 if it's not normal. So either way is fine with me. I probably personally would say there doesn't appear to be any outliers. Therefore, a sample size of 18 is okay. But as long as you mention the sample size, I'm not going to be picky. And just like as long as you mention the 5% of the population and you, I just want to make sure that you're mentioning every step, that you get them all. Does that help? Does that make sense?
Yes, thank you.
Yes. Thank you for asking that. Okay, let's go get through here. All right. So here it shows number 5 is good. This is a good way. I would absolutely, this is a perfect conclusion. If you typed that in, it's beautiful, it's perfect, it's lovely. I would accept that. The test statistic is greater than the critical value, so we reject the null hypothesis. That is sweet, simple, to the point. Yes, their conclusion that's on the next page is a lot larger than that, a lot more words, but I'm going to accept this. I don't need flowery words. They did the p-value. Let me see. They didn't tell you. They just said it is less than. Once again, if you give me this, if you use p-value, 100% perfect. You'll get all the points for that. I'm not, as long as you justify your answer and you use the words, we reject the null hypothesis or fail to reject, I'm happy. Okay, then this is their final conclusion. Is that number 44? That was my last slide. Okay. Now we're still on our recording. Before I ask questions, I am going to say, yes, I think that in my email I said that this was the last live Zoom meeting. I will do office hours on Tuesday. It seems to have been really successful, so we will do office hours on Tuesday from 5:30 to 6:30. I will be in here, and this just drop in office hours, and you can come and ask questions, and we'll have our. I wish that we were in person. I could like bring donuts or coffee or pie or something so we could have a big party. You're welcome, Bobby. I wish that we could celebrate. This has been a really good term. I've very much enjoyed all of you. So I just want to say that it's been a lot of fun for me. Sometimes they get boring and this one's not boring. I've been really enjoying myself. I hope you guys have had a little bit of fun at least. At least a little bit, even though it's stressful and it's a lot of information. Hopefully there's a little bit of fun there. Okay. Any questions while we're being recorded? You're welcome, Bobby. You're welcome. Y'all are so great. Okay. Any questions for our recording? I'm going to turn off the recording. All you not here, missing out.